The key thing you need to do in order to do that is implement Jacobian. So the mesh object has a Jacobian method where you say, for a particular cell, give me the Jacobian. If you're paying close attention to what I'm doing, Jacobian is d little x d big X. So in principle, Jacobian is a function of space. The good news is if your change of coordinates is affine, so if your change of coordinates has the form ax plus b, which ours does, then the Jacobian is constant over each cell. So you really only have one Jacobian per cell. If your change of coordinates is not affine, which is true if your elements are bendy, it's also true if you have quadrilateral cells and the quadrilaterals are not all rectangles. It's also true, similarly for hexahedra, if you have hexahedra and they're not all axis-aligned boxes, then you have to do this as a function of position. But we don't, so we get to use the optimization that there's one Jacobian per cell. And so you have to implement Jacobian of cell using the formula for this, which is 5.12. That one there, right up the top. And then once you have implemented 5.12, then you need to implement the integrate method of functions. So the integrate method of a function takes that function and integrates it over the domain. And it does that using 514, and 514, you'll notice, depends on 5.9. So sum over all the cells, and for each cell, the rule is this one. And this tells you the steps you need to do to go through that. And there's a hint here, which is if you really want to know how to do integrates, you can look through the code carefully and realize that there is, in fact, integration somewhere in the in error norm. There has to be. And so you can also get some ideas about how to do it from there.